This is an atmosphere-powered car. It works by using a syringe as a pneumatic spring to drive the rear wheels using these pulleys. In this video, I'm going to go through the fundamental principles behind designing such a car, such as the energy stored, the amount of torque produced at the rear wheel, and the theoretical range that this car should travel. And then, I'm going to take it to the next level. Let's start by addressing how this car is powered by the atmosphere. This is a syringe which I've sealed off the nozzle using an end cap, which when I pull the piston outwards, it expands a very small volume of air into a much larger volume, therefore creating a vacuum. Now this might seem similar to stretching a spring or rubber band, but the potential energy is actually stored in the atmosphere rather than the material it's made from. Because gases flow from volumes of high pressure to low pressure, it's not actually the vacuum inside of the syringe that is forcing the syringe to contract, but instead the atmospheric pressure pushing on the rear side of the piston. You might be wondering why I chose to expand the syringe using the atmospheric pressure to do the work, rather than contracting the volume of air inside the piston. Well, aside from the constant atmospheric pressure of roughly 1 bar, putting far less stress on the syringe than the infinitely increasing pressure of a shrinking volume, it also helps with calculating the stored energy, because there is a constant force exerted by the piston, which allows us to calculate the work carried out by the syringe. The unit for work is joules, which also happens to be the unit for energy, and work is calculated by multiplying a force by the distance that it's applied. By expanding this syringe, I'm applying a force over a measurable distance. I could measure this force, but it could cause inaccuracies due to friction, and the theoretical method of calculating it is way more interesting. Pressure is the measurement of force per area, and in the case of atmospheric air pressure at sea level, there is 101,325 newtons of force per square metre. So to work out the force exerted on the piston, all we need to do is rearrange the equation for the force, and we end up by multiplying the atmospheric air pressure by the area of the piston, which can be calculated by measuring the diameter of the cylinder, dividing by 2 to get the radius, squaring that, and then multiplying it by pi, which gives us an area of 0.000123 metres squared, and a force of 12.46 newtons, which is equivalent to hanging a 1.27 kilogram weight from the syringe handle. Taking into account that my current location is slightly higher than sea level, and there most likely isn't a perfect vacuum inside of the syringe, this 1.25 kilogram weight should be a good test to see if our calculations are close. Not bad. So we now know the distance and the force required to expand the piston, which when multiplied together gives us the work done in joules. Now I bet 0.56 joules means nothing to you, so to put it into perspective, this tiny AA battery, which is about the same size as the syringe, can store over 24,000 times that amount of energy. And for those of you who might believe that you can run your cars and aeroplanes on just thin air alone, if I were to fill this 5ml syringe with petrol, it will contain 320,000 times that energy. Now that we've calculated how useless vacuum-powered vehicles are, let's go through how we can get the most from the small amount of energy we've stored. As you'll probably know, to get the most efficient fuel consumption from your car, you're best off accelerating slowly and travelling at a slow constant speed to keep drag and frictional forces to a minimum. So this is where the pulleys come into play. Instead of the syringe producing a 12.46 Newton force over a distance of 4.5 centimetres, we can use these pulleys to convert some of that force into increasing the distance. For example, if the string was wrapped around a pulley half the diameter of the rear wheel, the force at the ground to rear wheel contact would now be halved, but the distance travelled would be double. This type of gear or pulley ratio is used in all sorts of applications, but probably most visible on a bicycle. When you ride a bicycle, you push down with your feet with a far greater force than you do when you walk. However, you travel much further per push. And in the case of this car, it has a ratio of 1 to 343. In other words, the 12.46 Newton force from the syringe is now converted to 0.036 newtons, or equivalent to lifting 3.75 grams. But in return, it should travel 343 times further, therefore theoretically travelling 15.7 metres. Now, I hope you found that interesting and all, but I bought a multi-pack of syringes from Amazon and I'm not willing to settle for just the 5ml syringe. So here it is, my atmosphere powered radio controlled car. It has a 100 milliliter syringe at the front here, which is 20 times the capacity of the 5 milliliter syringe. And interestingly enough, it can actually store 20 times the amount of energy in the atmosphere, which means that with these two syringe examples, the capacity of the syringe is directly proportional to the amount of energy it can store in the atmosphere. Now, as you'll probably expect from the start of this video, the larger diameter piston also means that there's a larger pushing force from the atmosphere. In fact, with this piston, there is a force of 79 newtons pushing it inwards towards the nozzle, which is equivalent to hanging an 8 kilogram weight from the piston, and it will just about stay there. Now, I decided to make a custom 3D printed piston so that I can attach a nylon string directly to it, which means that when it's fully extended to the outer position, there's not a huge handle sticking out the back of the car. Now, this nylon string is wrapped around an initial shaft of 5.6 millimeters in diameter, which drives a pulley that's 150 millimeters in diameter. This then drives a string which goes to a shaft which is 3 millimeters in diameter, which drives the rear wheel which is 170 millimeters in diameter. This whole pulley arrangement essentially gives the distance travelled by the piston to the distance travelled by the wheel a ratio of 1 to 1,518. So basically, this car should theoretically be able to travel about 197 metres. Now, I don't actually think this car will travel 197 metres for the simple fact that when you wrap the string around this shaft as many times as you need to, in fact, to pull this piston all the way back, the rear wheel needs to spin 369 times. The actual diameter of the shaft will be increased by quite a lot because it will basically be wrapping over the previous rolls of string. So that will actually reduce the pulley ratio the more you turn the wheel. Also, because I don't know how long this car's actually going to travel, and I don't have a really long stretch of really flat, perfectly smooth ground, I've decided to fit this car with radio controlled steering. So that way I should be able to test it in the house and be able to steer it round, hopefully. So let's go and give it a quick test after I've wound this rear wheel 369 times. Right, so I've only wound it up about 20 millilitres on the syringe gauge for now, so about 1/5 fully expanded, just because I want to give it a quick test. The string has already increased the diameter of the shaft by quite a bit, but this is going to be probably the smallest diameter test. Obviously, when I wind it up to 100 millilitre gauge, it's going to be really thick, so it's going to have a lot more torque. So I want to just test that it can run with this low torque amount, with the amount of string wrapped. Let's try this. Okay. Right. First test in 3, 2, 1. Slow start, slow start. It's picking up speed. Doesn't have much grip on those front wheels. That's working really well. Starting to, okay, and that's the end. Right, so I did what, 3, 4 laps? Now I'm going to wind it up to the full amount and we'll see how long this runs for. And we are fully wound back. Check how much string is wrapped around that thing. So as you can see, the diameter of the shaft has now increased by a lot. So I imagine it's going to be very fast at the start of the run. But let's give it a go. 3, 2, 1. Yep. Stop, 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 stop. Right. Oh no. The front wheels had no grip and it just went straight into the wall, tipped over, and then pretty much all unwound itself around all of this wheel, which is an absolute nightmare to rewind again because all these string is now tangled up. So I'm going to re-untangle everything, put some rubber bands on the front two wheels, and we'll give it another test in a minute, or in a few. Right, so I've glued some rubber bands onto the front wheels just to add some rubber grip. Hopefully this will allow it to steer properly and not just slam into the wall at the end. I've rewound it up to the 100 milliliter mark on the syringe, and I think we're all good for another test drive. I hope I'm not in the way of the camera. I'll move out of the way. In 3, 2, 1. Oh no. It's wheel spinning, it's wheel spinning. It wheel spins as soon as it goes around the corner. See that judder? Still got half the syringe to go. Okay, now it's reducing in the amount of torque it can produce, so it's not doing it as often. It's still got about 30% left, maybe. It's really slowing down with the amount of torque it can produce. Why is it not going? I think what's happening is the string is actually getting tangled because it's wrapped up so much, and it's making it harder to release. It's still going. Come on, come on. It's still working, just. Right, so I've just made a few minor modifications to it. I'm unable to change the pulley ratio currently, so what I've done is added 20 grams of lead to the back to increase grip, and also added another rubber band to the rear wheel. So we now have double the amount of rubber touching the ground and some downforce. I've also spent a bit more time winding the string around to try and get it as wide as possible on that shaft. The problem is if I have it too wide on the shaft, it may come off of this pulley when it's being wound up. So I think this is probably the best shot I'm going to get from this car. So yeah, let's give it a final test. Get my remote. And in 3, 2, 1. Oh, it's wheel spinning again. That's a really weird judder it makes. Trying to turn as slowly as possible so that it doesn't do it. Oh, that was smoother. As soon as it picks up speed, still going really well. Come on, now it's getting into its rhythm. If I just keep it turning and it doesn't have time to pick up speed, then grip doesn't seem to be an issue. Come on, don't stop yet. You still got a bit left to go. Okay, now I'm going to let it go a bit straight so it can pick up some speed, because it's running out of energy. Come on, the last little bit. You know you can do it. Come on. There we go. So yeah, it still has some winds left on the string, but it's not enough torque left to just... Still quite a bit of... See what I mean? There's still quite a few turns left in the wheel, which would obviously get it to that theoretical 200-meter distance. It just runs out of a bit of torque. So let's go back to the shed and conclude this project. So to conclude this project, I can confirm that the atmospheric pressure surrounding us is enough to power a small radio-controlled car like this. But I really don't believe that it's going to be replacing our fossil-fueled cars anytime soon, if ever. However, this was quite a fun project to do. I think there can be some improvements with this car, obviously to get rid of the grip issues. If I were to increase the gear rate, the pulley ratio, then that would reduce the amount of torque at the rear wheel and probably therefore reduce the amount of wheel spin. That would have to be designed into a version 2 car because these pulleys are the largest sort of pulley ratio I can put in this current chassis. As I said earlier, it's a 1 to 1,520 ratio throughout these two pulleys, and therefore to get larger pulleys on this, I would need to either extend the chassis or somehow move a pulley to the side of the syringe, and basically it would require a full redesign to reduce the wheel spinning. The main purpose behind this project was not to prove that we can replace our fossil fueled cars with atmospheric powered cars, because well, I think I've proved that's a bit ridiculous. The main reason behind it was to try and inspire some people to maybe try a similar thing. You don't need a 3D printer to build one of these, because I don't know if you've ever seen mousetrap cars. You can search them into Google and there's all sorts of examples, but it's quite popular in American high schools where they build a car powered by a mousetrap spring. Many people use stuff such as CDs as wheels and also balsa wood as the chassis, so you can build a similar car out of all sorts of different materials. I just thought the atmospheric thing with the syringe added a new physics element to the whole equation, so that now you can calculate the amount of torque it produces by the atmospheric pressure. Before I completely end this video, I just want to say something quickly. It's currently getting near to the end of 2018, it's late December, and this is going to be my last project video of this year. I will be working on new projects for next year, however at a slightly slower pace due to the Christmas holidays. I want to say a massive thank you to everyone that's been supporting my channel over the past year. I believe at the start of this year there were 46,000 of you subscribed, and it looks like we're going to reach 146,000 subscribers by the start of 2019, which is just insane that 100,000 of you have subscribed in the past year. I need to say a massive thank you to all of my Patreon supporters. I know I say this in every video, however they are the reason that I'm able to put the time and effort and also funding these things into making these project videos possible for the rest of you to watch. So huge thanks to you guys. I seriously couldn't fund all these projects without your help. Now there's one last thing before I shut off this video for the end of this year, and that is that I've made a compilation video of all of the projects I've done this year, because uploading videos on nearly a weekly basis for a whole year has yeah, it's brought about a lot of projects that I completely forgot I'd even done. So yeah, if you're new to my channel and you haven't seen any of my videos, then if you watch this compilation video and you see something, go check out my other videos. And if you've been subscribed for the whole year, then hopefully this will be interesting as a reminder of what I've been up to. Anyway, I'm going to go and enjoy my Christmas. Have a good New Year, and I'll see you in 2019. Merry Christmas, Happy New Year, and goodbye. Let's just spit it and then... Rotate the stick, should tilt the motors, and if I... Hey, it's flying! 3, 2, 1. Oh my god, that is so cool.